Enjoyed my time here at Queen's University. I think the education that I received was really great. The ability to do the capstone design project and the senior thesis and all that stuff is a real luxury that you all have in the engineering program. And also the pure physicists can do the thesis, so that's all very good stuff. So hopefully you're valuing your time here. It was certainly great on my end. So with that, I'll get into the presentation. So I'm here to tell you about growth in the fusion energy space and also the role of academic institutions. And I'll tell you the outline here. So the first half of the presentation is more about the field overall, why people are interested in fusion, why fusion is growing right now. It's actually a very exciting time to be in this program. And then I'll switch a little bit into technical challenges and what people are actually working on, and then spend the end of the presentation more specifically what we're doing at Columbia University and the role that universities play in general. So if I do my time right, it's about 4 bits of equal length. We'll see how I do, and I'll try and speed up if I'm running out of time. Okay, so the mission need for this program is basically to enable the energy transition that I hope many of you agree is something that needs to happen, and hopefully we'll see it happen in our lifetimes. We want to go from carbon-producing sources to low-carbon-producing sources, and we want to do this both for climate change and also for independence from petrostates, which we've seen in the news has been a big issue. So as physicists, well, there are actually things we can do, and in particular, the area of renewable energy and also nuclear energy is a big place that physics plays a role in this topic. So that's what motivates me in this area, and that's why I do this work. So this presentation is going to be about nuclear energy, and in particular about fusion energy. So we can actually get a ton of energy from the nucleus. You can see the binding energies here, and they're measured in megavolts. So there's just lots of energy per nucleon that can be harnessed, and you can do that by going from to areas where there's lots of energy stored. So you can go from high atomic numbers down, that's the process of fission, or you can go from low atomic numbers up, and that's the process of fusion. So again, because these are megavolts per nucleon, there's lots of nucleons in a nucleus, you just don't need very much fuel. That's the fundamental reason why you can fuel a nuclear submarine for years at a time with 1 dollop of fuel, or with fusion in particular, you can also just run the plant for a long, long time with not very much input fuel because you're getting megavolts out. A typical chemical reaction, which might be in a fossil fuel plant, is like electron volts per atom, something like that. So there's 6 orders of magnitude there. Okay, so I've tailored this presentation to people who are not working or thinking about fusion, so we have to start at the basics. And fusion has been known for a long time to be the holy grail of energy. Why do people say that? Well, basically, it is a thing that you can build and just plop it somewhere. It's a plant, and if it works, it'll produce energy. And so what that means is that it's dispatchable. You can put it to a place, and also it doesn't produce CO2. So these are all really good things. I told you already about the input requirements. They don't need very much fuel. The fuel can be obtained from seawater and also from lithium. I'll tell you a little bit about the role of lithium in a bit. And because the process is really difficult in the first place, there's really not any accidental risk of it running away from you. So in a nutshell, fission is easy to start and hard to stop. Fusion is difficult to start and easy to stop. So right now we're in the process of getting it started. I don't think anybody in the world is worried about what happens if we get it going and can't turn it off. There are a million ways to turn off a fusion reaction. So for that reason, we're excited about doing it. And I also like this picture because it's actually, in terms of the humanity's quest to control the atom, it's the missing quadrant. So we've been able to develop uncontrolled explosions based on fission and fusion. The historical development went from fission to fusion, where the modern atomic weapons are all based on fusion. And then on the controlled side of things, we have fission reactors. They're everywhere. But nobody figured out how to make a fusion reactor. So it's actually one of these big quests that humanity has been on for the last 50 years. And for me, that's an exciting topic. It's hard. It's big. Lots of different things are needed. But it's really a quest for our species to get right. So I start with a little bit of history. So atomic energy actually happened relatively quickly from the first weapons testing in the 40s. We went to the first fusion weapon in the 50s. And then actually the process from the first fusion weapon to the first fission plant, commercial plant, happened very, very quickly. So over the course of 6 years or something like that, with considerable funding from the military and from the government, we went to fission submarines and then also to fission commercial pilot plants. So the first question to ask is, well, why didn't we get it in the 50s or in the 60s? We were making a lot of progress back then, but it didn't quite work out. And this is why we get this comment that fusion is always 30 years away. It has been 30 years away. It will always be 30 years away. And the reason is that it's a difficult reaction to get going. So in the end, we need to create a box that harnesses the reaction inside and that you can extract the energy from. So there are some really fundamental challenges here. And I'll talk about some of these in more depth. So you need to control a plasma gas. Plasma is what happens when you take a gas and you heat it. The electrons and the ions go about in different ways. That's called a plasma. So that plasma needs to get heated to a very high temperature. The prototypes cost a lot of money, and that's just because you need to get them to be able to get to high temperature, and that takes quite a big box, and that box costs money. And then you also need to do R&D on several subcomponents. So these are all things that have to happen, and it's been taking some time for our program to get there. And so this has led to the perception that things are going too slowly, and this is kind of an area that you can ignore and be okay. So let's look a little bit more about the conditions that are required. So this is a picture of the cross-section for the fusion reaction. And you'll notice that you're in trouble when the unit is kilovolt. So even off to the left here, way too cold is 10 to the 7 degrees. But you actually need to get to somewhere, not quite 10 to the 9, but in the ballpark of 10 to the 9 degrees, 10 to the 9 Kelvin, which is 100 million degrees centigrade, or Kelvin. Very, very hot. Actually, you can do this. You can create a box and make a gas go to 100 million degrees centigrade, but that sets sort of the scale of the problem that you need. You also need to get high density, because that gives you, this is sort of like a barn for a cross-section, and so then the reaction is like the double product of the density onto that cross-section. So you need to get quite a lot of density for this reaction to happen at an appreciable rate. And so when you have high temperature and high density together, that means you need high pressure. So the name of the game is to get a high pressure, super hot gas into a box. How do you do that? So there have been two main approaches that have been pursued, and there's some hybrids, okay, but these are the basic ends of the spectrum. There's a magnetic bottle or a magnetic box where you use magnetic fields to basically keep the plasma in one place. These tend to look like rings because the magnetic fields are lines and they circle around and they spin in here. So these are magnetic approaches. And then quite separate are inertial approaches. So these inertial approaches are using radiation pressure from lasers to actually compress the fuel and then just use the inertia of the fuel to get that high temperature and high pressure region. Because these things are happening at 100 million degrees, you always need to get to 100 million degrees. They're always plasmas. So the whole realm of plasma physics grew up to understand how to get the conditions that you need for fusion to occur on Earth. So where were we in the 70s? Actually, it took a long time to understand the basic plasma physics of the phenomenon. And by the way, I'm paraphrasing, okay? We can talk a lot longer about this. But it took a long time to understand the basics of the phenomenon. And we think we understood at that point some of the building blocks. And so then there was a whole period of construction in the 70s and 80s. Okay? And those devices took some time to build. And then those devices were turned on. And actually, the results that we got out of them were not as good as we had hoped. And we, my parents and grandparents' generation of people. So they turned these devices on. They thought they would get a certain amount of energy out of them. Some energy came out, but it was not enough. And we'll talk a little bit about why, but basically, the whole field really had to come to grips with the phenomenon of turbulence. And anytime you turn on a kettle, you know the heat doesn't just gradually go up. It creates all sorts of a churning mass of blobs and things like that, okay? So that's the phenomenon of turbulent convection of heat, and that sort of thing ends up happening in a plasma, and it doesn't behave in an orderly manner. Furthermore, I'll add that around the time that this happened, the devices didn't look very promising, and also there was not a big societal need for energy at that time, and we'll return to this point a little bit. But the 90s were a period of relative good times on the energy front, and so fusion entered a period of what I call doldrums, where things were happening, people were studying what was going on, but there wasn't a big push. So things were kind of going slowly. And this occupied most of my childhood, I guess. So now we'll turn into what's happened in the last maybe 10 years or so. It's a little difficult to identify exactly when the gear switched, but there was sort of a new coming of age of the technology. And so now we see a remarkably different environment for fusion energy research. So we have new technologies that I'll tell you about that are offering less costly development paths. So that addresses this challenge of the unit cost of a prototype, brings that down. That's great. All that work that was done in the 90s really improved our foundational understanding of high temperature plasma, which is another important part of the field. And because of that, we've actually had some pretty good milestones in the field overall. the laser community has actually produced net energy gain from an injection of energy into a fuel pellet. So for a single burst of laser, that laser put in, I think, 2 megajoule, and they've gotten something like 3 megajoule of energy out, or 3.5 megajoule. So that basically shows that that approach is on a firm scientific footing, and then we're trying to get to that same level on the magnetic approach. So I'll just tell you a little bit. I don't work on the laser stuff. That sort of has a classified nature to it, so I do the magnetic stuff. So I'll be focusing in this presentation more on the magnetic stuff. But energy, anyway, because of these things, there's been a clear change in perception and support, and by support I mean money, into the field for fusion in the last few years. So I'll start with one very important story, and so this is the story of magnet technology. So we're trying to make magnetic confinement fusion. It's sort of a no-brainer that the better your magnet, the better position you have to actually make the high temperature reaction happen. So this group out of Massachusetts were very successful in actually deploying what's called high temperature superconductor into a large bore, really high performance magnet. So they were able to make, you see here in the news, about a 10-foot tall, 20 Tesla superconducting magnet. Actually, I think the field on the magnet can be even higher in different places, but you're sort of in the 20-ish Tesla domain. That's like an amazingly powerful magnet. And then I'll tell you in a second, that allows you to shrink the size of the device. And so that goes, why I have these pictures here. This is a different superconducting magnet for a project called ITER, which I'll mention in a little bit. But you can see these are quite large. Here's a bunch of dudes in the middle. And so this is 1980s technology. And this got you to about 10 Tesla or something like this. And so by deploying more modern technology, the size of the magnets can shrink. This is not exactly apples to apples, but the factor of 2 approximately is right. And so you can see the dimensional change in here. Okay, so stronger magnets enabled a size and cost reduction. So I'll give you a little bit on why. So you all done basic electromagnetics. Hopefully you know what a gyro motion is. So if I'm a particle living in a magnetic field and I'm charged, either positive or negative, I don't go straight. I actually spin around the magnetic field because the J cross B force does that to you. Okay, so particles follow these helical paths around the magnetic field. And remember, the magnetic field is kind of looping around the toroidal donut-shaped thing. So your kind of unit step size in a random walk process is that orbit width. So say I'm looping around and then I collide with my buddy, then I get bounced over to the next loop, and then bounced over to the next loop, and bounced over to the next loop. So the most characteristic size of your device is simply counted in orbits. So maybe I have a 1 meter device with 10 orbits. If I double the magnetic field, all of a sudden I fit 20 orbits inside that box. Okay, so without changing the physical size, I doubled the size that matters to the physics. And so whenever I have a system, say it was 1 meter, well, let's go the other way. Say it was 2 meters originally, and I shrunk it down to 1 meter, I've actually shrunk the volume by a factor of 8, because the volume goes like the cube of the linear dimension. So simply by increasing the magnetic field strength, you shrunk the volume by about a factor of 8. And if people get very fancy in terms of costing how much these devices should cost, the 0th order thing you can do is just measure the volume. Okay, so if it's like 8 meters cubed, it's going to cost $8 billion. If it shrinks to 1 meter cubed, it becomes $1 billion, because it's basically the volume, and it's primarily the steel actually that costs all the money. So simply by increasing the magnetic field, you've shrunk the device by a factor of 2, you've shrunk the cost by a factor of 8, and that gets a lot of venture capital people very excited, because then all of a sudden they see a path to build prototypes that are cheaper or within the budget of what a venture capital firm can do. Okay, so that's a little bit of a nugget on the magnetic field strength. This is a little bit of an aside, but the laser approach has also been making quite a lot of progress. It's a little bit of a friendly competition, actually, between the magnetic approach and the laser approach. I don't know what's going to win, because I don't know very much about high-power lasers, but other people do. So they're trying to improve their lasers. We're trying to improve our magnets, and it's a bit of a race to get to the end. And so in the recent last year, actually, this was a really nice result, and it made a lot of national news. And this was one of the few times when like a bunch of reporters would call me to be like, hey, what's happening in fusion? It's like, oh, hey, you care. Great. Let me tell you all the cool stuff that's happening in the field. And so this really raised the public consciousness on fusion, which I think was great. Just as another small aside on the laser guys, how did they get to where they needed to get? Well, do you all know The Martian? Okay, so in the face of overwhelming odds, they were left with only one option. They really had to understand their system. They built really complicated models, and they ran them on supercomputers. And it was really an amazing feat of experimentalists and theorists talking to one another. They really had to improve their understanding and think about, like, oh, should the fuel be this big or this big? Should the lasers come in at like this angle or that angle? Should they put more power at the beginning or more power at the end? Should they do a pre-shock? Should they do 3 shocks or 2 shocks? It's really complicated stuff, but they got to a level of understanding and coupled with experiment that they actually improved the performance of their reaction system by many orders of magnitude. So that's actually, for that group, been a major triumph. It took them 10 years, and maybe you think this is super slow, but the laser only fires about once a day for part of the year, so they were gathering data slowly as they went through that. Okay, so this was a big win for the laser guys, and I'm very happy for them. Okay, so plasma physics as a field was basically born to understand fusion. Plasma physics is also very important to astrophysics, but I think a lot of the impetus, especially in the 50s and 60s, was centered around controlled fusion. So sophisticated computer simulations have been developed, and they've been put together to understand the plasma state. And one of the big things that they have to understand is turbulence. So this is another picture of a plasma ring. Actually, I think this is looking the short direction, end on. Okay, so this is a nice movie, and what we're going to see is some turbulence develop. It's actually accurate, but it gives you a picture of what's happening. So that's a linear instability, and then it falls to pieces because nonlinear interactions come up, eddies come up, and then you get this process that to me looks just like what my kettle looks like, and that's convective heat transfer through turbulence across the magnetic field lines. So this process gives rise to heat transport that's in excess of like a classical prediction. And so this, in a nutshell, was not fully understood in the first generation of devices, and so they fell short because they didn't have all the information that they needed to understand the heat transport that they were going to get. Okay, I'll play it one more time if it goes. Yay! Okay, so there's turbulence really mucking up your thermal confinement. And that's called confinement, by the way, is like how well the energy stays in. So a system that's churning like that is going to be mediocre at keeping in the energy. Okay, so as a result of technological improvements, of which I told you about some, scientific improvements, of which I told you about some, there was a phenomenon that happened, which was that the private sector or the venture capitalists perked up, and they're like, oh, hey, maybe we're not too far away from the goal. You might also say low interest rates contributed. I do think low interest rates contributed because that allows you to have a lot larger risk tolerance. But in the end, we have this flood of new energy into the field following these achievements, both science and technological achievements. So now you can see this pretty amazing thing, which is there's this total bloom of companies. And probably the barrier to make a company is like the lowest it's ever been in the fusion space. Many people ask me, why didn't I make a company? Well, it's okay. We have enough of them already, actually. And they're all following different approaches. So they're following through on different shapes of magnetic bottles. Some are following through on the laser. Others are following through on hybrid approaches. So it's a little bit like the Wild West, but it's also lots of energy going into all these different concepts. So I think it's great. All these companies are going to get to really push the envelope on their approach and see what comes of it. So these companies, their logos are here. They all want to be SpaceX. Okay? SpaceX 10 years ago was not the company it is now. They were doing things that other people thought was impossible, and then all of a sudden it worked, and now they have a ton of money, and they're doing even more amazing things. So that's the analogy that people want to see happen in the fusion industry, that these companies are going to go from being kind of small operations that people haven't heard of to like really cutting edge enterprises. And I think this is a pretty cool thing. Maybe you all remember when this happened is when the rockets first landed for the first time. You're all old enough probably to remember that. And so that was cool. Nobody thought that could happen, and it's an inspiration to many people in doing hard problems. Talk a little bit about money. So the money going into the fusion space is huge. About $6 billion has gone into private fusion companies. And this, in terms of historical funding, is like probably more than a decade's worth, maybe 15 or 20 years of public funding all at once. So that amount of money is bringing forth a new level of investment and new levels of technology development. And what's interesting now is you can ask, well, is this a bubble and is it going to crash? Well, we're all physicists. It depends on how the thing actually works. Okay, so money is going in. They're going to build things. They're going to build boxes. We're going to see how hot the plasma gets inside. And many of the companies are not going to succeed, but hopefully at least a few do, and then they'll be the ones that carry the technology forward. One more comment. I didn't tell you too much about, so that's all like push from technology, but there's also societal pull. And the societal pull is something that's also been variable. Basically, the value that we assign to energy is, in my opinion, one of the most important things that sets the pace of alternative energy development. It's almost a no-brainer, but if nobody wants what you're selling, well, then you're not going to get very far selling that. So alternative energies really thrive when people place a high value on energy, and we're in another period of that right now because both climate change and also petrostate issues with various countries causing troubles for us. So that's another boundary condition. As long as those things are still a pull, I think you'll see investment in alternative energy technologies, both fusion and also other systems. Okay, so that's part one. What's fusion is an energy source with major advantages, but it's technologically very hard. Why are people interested right now? Because we've made advancements in the technology and on the science that's enabled a new era of both private and public investment. So now we'll talk a little bit about the challenges. So there's a lot of approaches being pursued. Let me just say, some are well-founded and scientifically mature. Others are rather speculative, and you can see the little picture here. There's lots of different approaches. I won't comment too much on the ones that I think are too wacky to work, but in the end, our research is focused on relatively mainstream approaches, and so we're working on magnetic bottles at Columbia and in my group. So these are magnetic bottles. We'll name them. It's a little bit jargony, but we have something we call a tokamak. This was developed in Russia in the 50s and 60s. It's basically a symmetric device. These are magnets. This came from The Economist, by the way. You know, when The Economist is writing about fusion, something is happening. So here's the picture about the tokamak, and then that's the plasma going on in there, which they politely call a fusion chamber. These are magnets. Okay, and then the stellarator is a twisty one. And basically, that twist can either come from currents flowing inside of the plasma or from the magnet itself. But you need a twist. That twist is important to keep the particles in the box. OK, so they look like that. They also look like donuts. So we have different varieties of donuts. Everything has to be a donut. And even some of the ones, by the way, that look just like cylinders, if you look closely, there are also donuts in there. But the donuts are produced inside the cylinder. So they generally tend to be donut-shaped. And this is because the magnetic field has to touch its own tail. OK, so I grabbed a movie for you all. So this is kind of neat. This is what it looks like inside of a tokamak. And so you're going to see some particles come in over here. Is my cursor showing up? Yes. And so that particle injection is going to light up the magnetic field. Otherwise, you don't see anything because it's too hot to emit visibly. But this particle comes in and lights up particular field lines. Looks like we got some lag. There it goes. Whoosh. So it's really like a swirling cloud inside of a donut-shaped box. That's maybe the best way to think about it. Here we go. One more time. OK, so there go the particles, and then there it lights up the field. So that's pretty neat. So actually, as like a box where crazy things happen, it's pretty interesting. Like you look in there, and all sorts of phenomenons are turning on. And Professor Morelli told you I look at off-normal events. Lots of like instabilities and things can appear in there, and little bursts and blobs and things. So it's pretty fun.
What's emitting the light?
This is line radiation, I believe, just from hydrogen. Yeah, it might be neon, but it's the line radiation. So it's just an excited high-Z atomic line. The camera is very, very far away, actually. Yeah, you can't. So it's looking through an incredibly long periscope with a bunch of mirrors. But they're pretty good at zooming in. OK. All right, so tokamaks are the ones that are the most far ahead. This presentation is going to start kind of zeroing in a little bit more and more as we go along, so from the big picture to specific concepts. The tokamak is the concept on the magnetic side that's the closest to energy gain. That picture that I showed you before came from a device that almost got there. It got to like, I think, 30 or 40% energy gain, not quite enough to break even. And what do I mean by energy gain? It basically means that the nuclear reactions inside of the plasma produce more energy than went into the plasma. Okay? That's a scientific metric for energy production. It doesn't count like the energy that heated the magnets and all that, but that's like the scientific baseline for an energy producing system. You actually need to show energy gain of like 10 to make an economic system, but energy gain of 1 is thought to be the next important step. So there's different facilities under construction. This is one in France called ITER. It's being put together by the public sector. It's the one that I showed you with the big magnet. That's that same type of magnet there that had those people standing in the middle of it. Okay, this thing's coming together in France. And then this is one being led by the private sector by a particular company I'll focus on for the rest of the presentation called Commonwealth Fusion Systems. This one's being put together in Massachusetts. And this is the other, this is the technology based on the high temperature superconductor, so the dimension is smaller. Maybe it's hard to tell, but that's a smaller crane than that one. Okay, these are still plants. They're still building-sized things, no matter what. Okay, if you all like space, so there's a nice analogy with space missions. So the publicly funded program is doing something quite analogous to the Space Launch System. Much more expensive, slower, still worked, still pretty cool. And then the private sector is trying to be SpaceX. I already told you about that. So there's the Falcon Heavy, which is like the analogy of these two projects that I showed you before. So where we are in fusion is before these pictures, right? These pictures show a public system launching, expensive but it works, a private system launching, cheap and it's amazing. They're both launched. In fusion, neither device has been finished to be put together. They haven't launched yet, so we're not quite at the level of this picture. And Starship is only on paper in the fusion system. Okay, there is the analogy with Starship, which would be the next thing, but that is only existing as a cartoon at the present time. Okay, so let me go into a little bit more about challenges. How are we doing on time? So one thing that we need to do is achieve high plasma performance and control. And so this is indicated by this nice picture here, which shows progress in years against what's called the triple product. This is like the criteria for fusion success. It's the density, the temperature, and the confinement. So if these three things are multiplied into one another, they get above a certain level, you have an energy-producing plasma. And so you can see that progress is being made by these different approaches. The red one is the tokamak. It actually saturated because the unit cost of the prototype got too large. And so here we are with where we expect ITER and Spark, and it's sort of been taking too long to get there. Other approaches are making progress. Here's the laser. They're actually arguably ahead of the magnetic approaches. Okay, and so it's important to be able to predict performance. And so when you look at like core plasma physics, the sort of basic three building blocks that we have the understanding of the turbulent transport. That has to be kept to a low level, and we have a number of tricks to be able to do this. We have to understand the macro stability, which is the problem that I primarily work on, which is basically can the plasma stay in one piece and can it stay happy? And then you have to understand the exhaust of that power. So basically, if you're successful, that plasma is producing a lot of power. It can melt things if you're not careful. So that's that problem there. Coupled to power exhaust is actually plasma-facing materials. So if you're successful and you have this really radiant, high-energy gas, it actually looks a lot like a metal blowtorch. That's bad. You don't want a metal blowtorch next to metal. So there's lots of people working on both improved material boundaries. They tend to be high Z refractory metals, such as tungsten is pretty good for a material boundary. And so we're understanding how to minimize the heat coming out, how to basically spread the heat over a larger area. And also there's another area of the field which is looking at liquid metal solutions. This is kind of funky, but perhaps by melting the wall in the first place, then you can do better on the boundary solution. So this maybe the liquid metal wall is like maybe one step lower technical readiness. So there's more fundamental research needed there. Wanted, better materials. So if anyone is doing material science, there's a lot of interesting work to do here. The other challenge is on the fuel cycle. So the fuel for these reactions is primarily tritium. Tritium is produced in CANDU reactors here in Ontario and other places. And you can also extract tritium from what's called a breeding blanket. So most people foresee fusion devices being surrounded by a shroud of lithium. And that lithium is where the neutron impacts the lithium and makes some tritium. So this is actually a pretty big research area. I think there's a lot of open questions here. And my 2 cents is actually there's a big opportunity for Canadian nuclear engineering and Canadian industry to get involved in this problem because there's a lot of open R&D questions. Right now, this is not super active. It is active, but not at the level we need it to be. And my 2 cents is that I think this is an area that will really blow up once the scientific energy gain is demonstrated in a plasma, because that will sort of be the next step on the critical path, although there is work in parallel to get ready for that. Other solutions that people are thinking about are liquid salts, so you can actually put this in there. This actually looks a little bit like a fast reactor, which is also surrounded by molten salt, and also doing pebble beds. So this becomes a lot like a sort of nuclear engineering problem in this area. Okay, so there is an analogy here with fission. So at the dawn of the nuclear submarine program, many of these questions kind of have a ring to them that might sound familiar. Nobody knew how to design the material for the cladding of the fuel. That's exactly the same thing as the plasma material problem to 0th order. Nobody knew how to process the uranium into fuel rods. Actually, not only did nobody know how to do it, nobody knew it would even be possible, but they still did it. Okay, so they still worked towards a solution, and there was also issues of aligning the public sector and the private sector working towards a big societal goal. They had the benefit of the military-industrial complex behind them, so it happened a little bit faster, but there was still the same basic ingredients there. So there were no guarantees that solutions existed, but institutions, entire laboratories worked towards the solution, and they got there, and they got there relatively quickly. And if you look at the history of this program, people were actually surprised it worked, okay? But they got there. Now let me turn to universities. So at universities, we're not out there to make a profit. We're not out there to patent a particular reactor design and sell it to the country or whatever. We're actually looking to work at a more fundamental level. So we're the incubator of really the fundamental ideas that are then being exploited in different companies. We incubate the talent that produce the workforce for these companies. So at Columbia, actually, many of our alumni are leading the fusion industry charge. And we also are producing worker bees that staff all these different companies. So at all different levels, the universities produce the people. And many of these challenges that I described are actually fundamentally multidisciplinary. They connect nuclear engineering, physics, material science. So that kind of interconnectivity tends to happen at the university because they have all these different bits and pieces. Of those 40 companies, most of them came out of universities because the people there, maybe they had latched onto an idea and then they wanted to see it go through at a company. Okay, this is our group at Columbia. So we have about 5 core plasma faculty. You can see the numbers there. We're a pretty large group. And actually, we benefit from one of the largest labs on campus. New York real estate's quite expensive, but historically speaking, we just happen to occupy the whole basement of the building, and so we have a lot of square footage there. So all these folks are working on different parts of the problem. Let me tell you a little bit about overall what we're doing. So our plasma fusion program has sort of 3 different thrusts. The first 2 I'm just going to mention. I'm not going to spend very much time on, but we have on-campus plasma fusion and technology experiments. So we have 2 tokamaks of different sizes and a little stellarator in this vacuum chamber. There it is there. It's pretty in pink. And so what we do with small experiments is prototyping, basically. So you're not going to put a thing on a big nuclear device for the first time and hope it works. You do small-scale prototypes at small scale, and then you can basically see if your basic approach is sound. You can see if the measurements are going to work. So there's like a hierarchy of tests. As you get more advanced, they're more expensive, and you have to wait longer. So the first time you do something should be at a small-scale facility. And that's what the role of the on-campus is. So these are like the lowest technical readiness level type experiments. Particularly, we do a lot of control research, so we understand how to make our actuators work better, and we do actually some fundamental alpha-vane wave physics on these guys. Another big part of our work is what's called user facility work. So there are large-scale user facilities. These are tend to be about one or 2 per country, and so these are larger scale plasma devices. You can see these are both tokamaks. This is the one that's not built yet. This one exists, and so we can conduct experiments on these facilities and basically take our understanding to the next level and see if the phenomenon that we observe at small scale is then appears at the next level of scale. In terms of size, These might be like a quarter size or so, maybe a fifth size of where you think you'll end up. These are like a half size of where you'll end up. This one's too big, and the one that we're hoping to make is about twice the size of this one. Okay? So this is another part of our program, and this is all in the publicly funded program. The rest of the presentation, I'll actually talk about how we support private industry. Why is that? Well, it sort of followed with the flow of the presentation, and it's a little bit easier to describe. So we do quite a bit of industrially sponsored research at Columbia, and this basically means the company gives us money to answer questions that they need answered for their concept. We do that with a bunch of different companies, and so that's what we're going to talk about. And there's also some public cost share program. This is where the company might pitch in $1 and the government pitches in $2 or something like that, and then they can use our services. So we'll focus on our contributions to Spark. So this is one that I showed at the beginning. This is like the Falcon Heavy type project that people are hoping will happen faster. This is being built. Whoa, what's going on there? Oh my goodness. Look at that. That seems to be okay. I lost my mirroring. That's okay. So the goal of this project is actually to produce energy gain from a tokamak device in the near term. And so what we do here is we basically produce calculations that are not something they can do in-house because they don't have the tools, they don't have the expertise to do those calculations. I would argue they shouldn't have that expertise because it's just too specialized, right? They don't need a full-time person to do this calculation. They need to contract that out, use somebody else's expertise. It only costs them like 1/10 of their time, and they give them all the value that they need. So that's sort of our role in the academic atmosphere, is to have the expertise that's valuable to a company such that they can contract with us to produce that calculation. And by the way, we do it for multiple companies, so that's how we make our operation work. This is a picture of us in front of it. That's some of my research group members. This is the factory, this is the building where it's being housed, and this is the warehouse where it's going to go in. That's what it's going to look like, but it's not put together yet. Okay, so going a little bit more technically into what we're doing. So this thing is basically a big hunk of metal with a lot of magnets all surrounding it. So it's one enormous electromagnet. That's the way to think about it. These are the toroidal magnets that make a field that goes a long way around. The plasma itself is actually well described by the equations that describe metal. So the plasma is a metal. It's a less conductive metal. It's a highly conductive metal. So what that means is that there's resistivity, there's Ohm's law works in there. And then the magnets themselves are described by electromagnetism. So electromagnetism is really like the foundational building block of magnetic confinement fusion. Okay, so we're going to show you a few highlight calculations of what we do to understand this electromagnetic system. So one big topic is called pulse design and plasma control. And so this basically, to zeroth order, you have these electromagnets. What voltage am I going to put on them at what time? And how is that going to make a plasma in the middle? Okay, so these are simulations that allow these currents, and these are the electromagnets here. They're turning on at different rates, and then you can see the plasma being formed. We have actually electromagnetic models of the surrounding conducting structures here, so you can see different color codes appear. I wonder if I can make this play again. Is that going to go? No. Oh, well. You saw it once. So the circle got bigger and smaller as the... There we go. Good. Okay, so you can see the colors change. That's showing different induced currents. And so we're basically using the Faraday's equation both in the plasma and outside of the plasma to understand the dynamic evolution of the plasma. Why do we care about that? Oh, by the way, if anyone wants to play with these tools, it's all open source. So this is our toolkit, Open Fusion Toolkit. You can maybe take a picture of that and play. You can download and run these kind of simulations on your laptop. Why do we care? So this is a very hot plasma. If it moves too far to the side, it melts things. Okay, that's the fundamental thing. You want to keep it in the middle. You want to keep it well controlled. And so we can study, for example, with a certain array of sensors, these dots are pickup loops. And so these pickup loops pick up the various components of the magnetic field, and they tell you what the plasma looks like and where it is. And so we study, as an example, What happens if you lost half your sensors because somebody tripped over a cable or maybe they got melted or something like that? Can you still position the plasma accurately enough such that it doesn't melt its surrounding area? So that's an example shown here. This is a pretty good level of control with 10% of the sensors lost, with 40% of the sensors lost. Maybe it's marginal. So that informs redundancy needs on the sensors. How am I doing? I'll skip that one. This is instability detection. So I told you that the plasma can develop instabilities. I didn't tell you that those instabilities tend to look like helical ribbons. So this is the long way around the device again. And you can see there's like a current that looks like these interesting helical ribbon. And so here we're running a simulation where we look at what that helical ribbon is doing to the surrounding metal. The surrounding metal is also conductive, so that conduction produces induced currents around the outside. Okay, this is again a fundamentally electromagnetism problem, time-dependent, three-dimensional electromagnetism. Why do we care about this? So these plasmas are surrounded by sensors, so we can tell based on these simulations what is the minimum size of an instability that you can detect. Okay, if it's too big, it's bad. Can we detect it before it gets too big and do something that we think is useful to stop the instability from getting any bigger? And that informs our ability to treat what's called soft landing or basically healing of a sick plasma through various means. Once the plasma gets really sick, you just turn it off and you start again. Okay, so they can be quenched very quickly and then come back. So this is another slide on our study of rapid quenching. So if a plasma is quenching very quickly, actually the current that's flowing the long way around the device will be shut. That, if you remember your Lenz law, if you have a big change of current, you're going to get a big voltage because you have to keep that flux going. And so that voltage drives a big induced current in the surrounding structure. And that's actually the worst case scenario structurally for these things. So if you have too quick of a current arrest, all that induced current is going to flow in the wall. And that produces J across magnetic field B. And it's like a tin can experiment. You know, if you've ever done that aluminum can, okay? So you don't want that to happen. So these calculations tell you how thick the wall needs to be so that it doesn't get crushed like an aluminum can. These are all eminently practical questions. If you're actually designing a system, you don't want it to be destroyed like that. Okay, so if you're not smart, you'd make it too thin, but we have calculations that allow us to specify how thick the wall should be. I didn't tell you here, but you can see that our publications are out on this topic, so you can read more about that. Okay, so my last comment is a little bit on applications versus foundations. So you might see from the last few slides, it's all very applied, right? So when we do work for private industry, they don't want us to go down a rabbit hole of like, what's the best thing? They want to know how thick to make their metal. They want to know whether the magnet should be positioned accurately or not accurately. They want to know how many sensors are there. It's all very practical, industrial-sponsored research. There is a whole other side of the work we do that is in service of the public sector, which is much more open-ended and foundational. So a question there might be like, well, you know, here it is. Is this really what it should look like? Maybe it should look more like a square or like a triangle or like a oval, who knows? So those are all more open-ended questions. The company doesn't actually care about that because they've already built their thing, or they're in the process of building their thing. So they're interested in much more detailed questions. The work we do in the public sector is more open-ended and is more curiosity-driven, I would say. So there we're really looking for the best possible solution. My comment here is that as long as the stuff that's being built now sort of works, it doesn't have to be the end look of the system. We expect multiple generations of these systems to come through. If you look at fission, you know, Gen 1, Gen 2, Gen 3, they had different changes in each design iteration. So we can do both in parallel. We can basically make the thing that's in construction work with understanding that it might not be the most optimized situation, and we can also do curiosity-driven research to look for what the best configurations are. So there's much room for exploration. There's much fun to be had. If you want to be doing applied work, you can do applied work. Curiosity-driven work, you can do curiosity-driven work. And usually, actually, the same people do both with different fractions of their time. So that's kind of the end. So I told you a bit about the technical approaches and challenges. We have magnets and lasers. We need to get high-performance plasmas. We need to get good materials and a fuel cycle solution. And at Columbia, we're using targeted calculations to accelerate the design and assembly of the first generation of net energy devices. We expect those to be turned on this decade, actually in the next handful of years, maybe not quite sure exactly when. And we do expect that design cycle to improve in future cycles also. So that's it. Go back to the beginning. What's fusion? Energy source with advantages, but it's hard. Why fusion now? We've had good advances in technology and science. It's given us a lot of new money and a lot of new energy. And the rest I just said, so I won't repeat it again. But thank you very much for your time, and I gave you your 9 minutes back.